Year 13 Revision Video 1. This revision video will cover 4 different topics: differentiation, integration, trigonometry and parametrics. It will look at a different question on each of these topics, sometimes with connections between topics as well. You should read the question, try the question yourself, and then use the video either to check your answer or to access support if you're not sure how to do the question. You should then make sure you try the same question a few days later to see whether you've learned how to do the question correctly, if you weren't able to do it yourself correctly the first time. So here's our first example. The equation of a curve is given by y equals 2x over ln x. Show that the only stationary point on this curve is a minimum point at e to e. Now, look at the marks available here. 9 marks. That means there is a lot required of us, and we must show detailed reasoning, which means we must show our work very clearly. Now, we know, to begin with, we need to differentiate this function, and it's set up in a way that suggests the quotient rule is going to be our best option. So that's when we want y set up in the format u over v, where u and v are separate functions of x. So the numerator, u equals 2x, which means du by dx is equal to 2. V is the denominator, that's ln of x, and dv by dx is equal to 1 over x. And then we can very clearly write down that dy by dx is equal to v times du by dx minus u times dv by dx all over v squared. There's our formula for the quotient rule. So starting off with v times du by dx, that's the product of these two, and that will give me 2 ln x. I want to subtract from that u times dv by dx, so that's the product of these two. And of course 2x multiplied by 1 over x will simply just give me an answer of 2. All of this is over v squared, and for clarity I will write that as ln of x all squared. Now, we then need to identify stationary points, so I'm going to do that in the next part of my working by setting dy by dx equal to 0. So if dy by dx is equal to 0, this then tells me that 2 ln x minus 2 over ln of x all squared equals 0. Now multiply both sides by the denominator, and we have 2 ln x minus 2 equals 0, or alternatively, just thinking logically, the only way we're going to get a 0 out of this calculation, out of this division, is if the numerator is 0. This then gives me ln of x is equal to 1, so x is equal to e. Now, we need to find the y-coordinate as well. The question gives us a full coordinate, so we need to substitute this back into the original function, y equals 2x over ln x. That's 2e over ln e. ln of e is 1, so that gives me y equals 2e. So here is my coordinate of the stationary point, e to e. Now it's the only stationary point because there's only one root to this equation. There's only one number that gives us an answer for x that forms the solution of dy by dx equals 0. We now have to show that this is a minimum point, and the temptation will be to find the second derivative because often that's the easier way of doing it. Now that means you would have to apply the quotient rule for a second time here, which can be done, but this is a much more complex function now, and you are more likely to perhaps make a mistake. So don't forget that you can identify whether something is a maximum or a minimum by looking at the sign of dy by dx either side of the x value here. And that's the way that I'm going to do this. So I'm going to set up a little table which contains x values and the values of dy by dx evaluated at those x values. Now we know that at x equals e, 2 ln x minus 2 equals 0. the gradient is equal to 0. So that's when we're at 2.718 ... dy by dx equals 0. So I'm going to evaluate what happens when x is equal to 2.7, so slightly less than e, and when x is equal to 2.8, and that's going to give me an idea of the gradient. Now, there are so many ways I can do this very easily using the graphical calculator. One way in which I can do this is to store 2.7 to start off with as x, using the arrow key and the x key, which is just underneath the alpha key there. And then I simply input the dy by dx calculation in terms of x. So I simply use that x button again, write this out, and it stops me from having to keep typing in the number 2.7, which is where I might be likely to make a mistake. So this tells me that the gradient is equal to negative 0.0136 ... So that is a negative gradient there. Now, I then simply replace 2.8 as the value of x on the calculator, and then I use the arrow key to scroll upwards and then just evaluate the calculation again. And this time I find that at x equals 2.8, dy by dx is equal to 0.05587, so it's a positive value. So we've evaluated the gradient at x equals 2.7 and at x equals 2.8. Notice I have actually written down the values of dy by dx that we have found, because the question required that we show detailed reasoning. So this then tells me that the pattern for the gradient is that it starts off negative, it's then 0 at x equals e, and it's then positive after that, which means that we have a minimum point. And it's clearly demonstrated through our use of the gradient here. Now, alternatively, some of you may have chosen to find d2y by dx squared, in which case you would have had to use the quotient rule again. This time the numerator is 2 ln x minus 2, so du by dx is equal to 2 over x. V is equal to ln x squared, and to differentiate v, you've then got to use the chain rule. You could also use the product rule, but that requires a little bit more working to be written down. So dv by dx, well, I would have a look at that and I would say, well, this is a function being raised to a power function. So to differentiate it, we simply multiply by the overall power, which is 2. We reduce the power of the function, the overall function, by 1, so 2 drops down to a power of 1, and we then multiply by the derivative of the inner function, which means we multiply by the derivative of ln of x, which is 1 over x. So this tells me that dv by dx is 2 over x ln x, like so. So remembering our quotient rule for differentiation again, we start with v times du by dx, so that's the product of these two. So that's 2 over x ln x squared. And we then want to subtract from that u multiplied by dv by dx. So that's 2 ln x minus 2 multiplied by 2 over x ln x, and then the whole thing is over v squared. So that's all over ln of x to the power of 4. And we then need to evaluate this at x equals e. So this gives us 0.7357, which is of course greater than 0 or positive, which implies that the point E to E is a minimum point. And again, notice the level of working I've shown in my answer here. We are required to show detailed reasoning. We must show that working very clearly. So the next question is an integration problem. So integration is always more complex than differentiation, and we have to think through the methods very, very carefully. Now, this is a very standard type of integral in that if you see an integral like this, an integral of the form x squared sine x or x squared cos x, this has to be done using integration by parts. Substitution, other methods will not work. So it's going to be integration by parts. It's also actually quite a complex integral, and you will see as this pans out that it's going to involve using integration by parts twice. So to start off with, I would like to remind myself of the integration by parts formula, which tells us that the integral, the original integral, is made up of a product of two components. One component is u, the other component is dv by dx, both being integrated with respect to x, and the integration by parts formula tells me this is uv minus the integral of v du by dx. So the idea is one part of the original expression being integrated stays the same here, but is then differentiated here before the second level of integration. And then another part, dv by dx, is integrated here and here before the next phase of the integration. So let's look at the two components here. We've got 4x squared and we've got sine 2x. So those are the two components. Now, we need to choose the trig function to be the function that is integrated, because otherwise 4x squared will just become more and more complex as it's integrated, whereas a sine function just becomes a cos function when it's integrated, and that doesn't make it any more complex than it already is. So u is going to equal 4x squared, which means du by dx is going to equal 8x, and dv by dx is going to equal sine 2x, which when we integrate it, you actually now have to use a little bit of integration by substitution here, but we're going to do this the quick way, where we recognise this is a sine function, so it integrates to negative cos 2x, but you need to divide by the derivative of this inner function, so it's minus a half cos 2x. So my integral becomes uv first of all, so that's the product of these two. So to tidy that up, minus a half times 4 will give me a minus 2. I'll leave the x squared at the front, cos 2x, minus, we'll put the minus sign in for the moment and then deal with anything that comes up in a second, the integral of v times du by dx, so that's the product of these two. So minus a half times 8x will give me minus 4x cos 2x, and of course there is a dx, which actually I should have written up here in the integral there, because we are integrating with respect to x. So I'm now going to tidy up my working a little bit, because of course the minus minus here can just be rewritten as a plus, and then I will leave the 4x inside the integral here, even though we could pull the 4 outside if we wanted to. So now you can see why this has to be integrated by parts again, because we've got a 4x and we've got a cos 2x. So we've got to start the integration by parts again, a second time over. So here's what I'm going to do. I'm going to set everything up in the same way again. U is going to equal 4x. Du by dx is going to equal 4. dv by dx will equal cos 2x, which integrates to a half sine 2x. Cos integrates to sine, and of course you need to divide by the derivative of the inner function again, which is just 2. So let's keep going with this. So the first part of my integral is just as above, and then I'm going to now fill in the integration by parts of this portion here. So we want uv first of all, so that's the product of these two. So again, 4 times a half will give me 2, so that's plus 2x sine 2x. And then remember it's subtract the integral of v multiplied by du by dx. So multiply these two together. Again, the 4 and the half will simplify to give me a 2. So 2 sine 2x dx. And I still haven't finished because we now need to integrate this portion here. But that is a standard integral that we can do very easily. So my first two terms are as before, no difference there. And it's this blue integral I now need to finish with. So sine integrates to negative cosine. So the negative sign is going to vanish in a second. This will integrate to cos 2x, but of course I have to divide by the derivative of the inner function, which is 2, which will then cancel with this 2 here. So it's just plus cos 2x at the end, and then of course we mustn't forget to include our plus c at the end of all this. So my answer is negative 2x squared cos 2x plus 2x sine 2x plus cos 2x plus constant. So our third question is a trigonometry question. Part 1 requires us to know the exact values of tan 45 and tan 60. These days, obviously, a good calculator will give you those values straight away. You could, of course, also sketch your special triangles. Now, tan 45 degrees is equal to 1, and tan 60 degrees is equal to root 3. Now, part 2, we must show detailed reasoning here, and we've got to show that tan 15 equals 2 minus root 3. Now, why is the detailed reasoning comment there? To stop somebody from plugging in tan 15 into their calculator and potentially getting 2 minus root 3 as an answer, which is indeed what your calculator would tell you. So, let's work this out properly. What is the link between 15, 60 and 45? Well, this question is all about understanding whether or not you as an individual know your trigonometric identities, which ideally you really should be very, very familiar with. So the connection is obviously that 60 subtract 45 is 15. So tan of 15 is equal to tan of 60 minus 45, because 60 minus 45 is 15, so the left-hand side and the right-hand side are indeed equivalent. You're then expected to use the identity for a tan compound angle formula. So tan of A minus B is equal to tan of A minus tan of B all over 1 plus tan A tan B. So we simply replace A with 60 and B with 45. So this is tan 60 minus tan 45 over 1 plus tan 60 tan 45. Now, tan 60 we know is root 3. Tan 45 we know is 1. And this is all over 1 plus tan 60 times tan 45, which is just root 3. And this then becomes a surd problem, and we're going to rationalise the denominator here, multiplying both the numerator and denominator by 1 subtract root 3. And this is a point at which you can of course get your calculator to double check and verify your working here, but we are going to write down the full calculation to make sure we've shown our working very carefully. So expanding in the numerator, we will get root 3 minus 1 plus root 3. And the denominator, of course, we are going to get 1 minus root 3 plus root 3 minus 3. So all that remains is for me to simplify my working, which I will do now. So my numerator is going to give me 2 root 3 minus 4. And my denominator, well, my central terms obviously cancel out. And I'm left with 1 minus 3, which is negative 2. And of course, you can now see that dividing both terms in the numerator by negative 2 will give us the 2 minus root 3 that we were required to get to at the end. So our final problem involves parametric equations. We're given x equals cos t minus 3t, y equals 3t minus 4 cos t minus sine 2t, and we are working with differentiating trigonometric functions, so we have to be working in radians. So the question says, show that the gradient of the curve is always negative. So there's a bit of problem solving going on here. We're not being instructed very specifically as to what to do with these functions, but it's clear it's got something to do with the gradient. So let's start by differentiating. So dx by dt is equal to, now differentiating this function here, cos differentiates to give me negative sine, and then I have -3 at the end. Now, differentiating the second function here, dy by dt is equal to 3 plus 4 sine t, and then for this last part it's going to be -2 cos 2t. Think about why that is. A sine function differentiates to a cos function, but we need to multiply by the derivative of the inner function, which means we multiply by 2. For the central term, cos differentiates to negative sine, so hence we lose the negative overall. Now, we then need to remember our chain rule, which tells us that dy by dx is equal to dy by dt multiplied by dt by dx. Now, dy by dt is here, so that's 3 plus 4 sine t minus 2 cos 2t. And we're multiplying by dt by dx, which is of course the reciprocal of that. So rather than writing times 1 over, we'll just put this in the denominator. So here is our derivative dy by dx. Now, it's easy to see that the denominator is always negative. And that's because we're defining this for t values between 0 and pi. And if you think about the sine function between 0 and pi, sine t will always be positive. So sine t will basically be between 0 and 1 for this particular set of t values. So negative sine t will be between -1 and 0. So the denominator is always going to be negative. Now, the numerator, I'm going to look at the fact that we have cos of 2t here, and we know that there are identities that link cos with sine, in particular the double angle formulae. We know there is an identity that tells us that cos 2t is equivalent to 1 minus 2 sine squared t. Now, how do I know to use this particular version? Because there are 3 identities for cos 2t. Well, I know this really, or I have an inkling that I need to do this, because this function here is sine. Had it been cos, I would have used a different identity for cos 2t. So let's now investigate the numerator in more detail. So I'm just going to separately write out 3 plus 4 sine t minus 2 cos 2t as 3 plus 4 sine t minus 2, and then in place of cos 2t, I'm going to write 1 minus 2 sine squared t. And then I'm going to expand and simplify all of this. And when you do the algebra here, you will see that you end up with 4 sine squared t plus 4 sine t plus 1, which you can see factorizes. And it factorizes to 2 sine t plus 1 all squared, which means that the numerator is a perfect square, which means that the numerator has got to be 0 or above, essentially. If it's a perfect square, it cannot be negative. So the numerator cannot be negative, the denominator is always negative, which means that the gradient overall will always be negative. And that tells us that dy by dx will always be negative.